something moved in the blackness. At first, it was nothing more than a faint flicker on a digital sky map, a single point of light that didn't belong to any known star, asteroid, or comet. The date was the 27th of August 2025, when the automated telescope array of the Asteroid Terrestrial Impact Last Alert System, or ATLAS, picked it up during a nightly scan of the southern sky. Within hours, the algorithms flagged it as an anomaly. It wasn't moving like a regular comet, nor did its trajectory curve with the predictable arc of a solar-bound visitor. The data didn't fit anything in the catalogue. By the next morning, astronomers were awake across Hawaii, Chile, and Europe, each downloading the same strange set of coordinates. The object was dim magnitude 19.3, barely visible even through the most powerful scopes, but its motion told a story. It wasn't orbiting the sun, it was passing through. Its path, when traced backward, didn't intersect any planetary body or the outer regions of our Oort cloud. Instead, it originated far beyond, from the interstellar gulf between stars, a visitor from elsewhere. They gave it a name, 3I Atlas, 3I marking it as only the third confirmed interstellar object ever discovered, after the infamous Oumuamua in 2017 and Comet 2I Borisov in 2019. But unlike its predecessors, this one came carrying a sense of intent, a direction that didn't seem accidental. It was inbound from the constellation Hercules, cutting through the ecliptic plane at a shallow angle, moving at an astonishing 39 kilometers per second. If that sounds fast, that's because it is fast enough to cross the distance between Earth and the Moon in less than 3 hours. From the start, 3I Atlas felt different. Oumuamua had been strange in shape, tumbling like a shard of glass, and Borisov had behaved more like a regular comet, shedding ice and dust as it passed. But Atlas was quiet, no tail, no coma, just a smooth, steady glow that didn't change for weeks. To most instruments, it looked like a solid fragment, dark, carbon-rich, and oddly reflective for something so deep in space. The more they tracked it, the clearer it became. This was no ordinary comet from the frozen outskirts of our system. In the first weeks of observation, researchers at the European Southern Observatory began comparing its light curve to known cometary models. It didn't match any of them. The albedo, the measure of reflected sunlight, was too high for a dormant rock but too low for an icy body. Its spectral signature hinted at a surface coated in complex carbon compounds, something akin to tholins, organic molecules forged in radiation-saturated environments, the kind we associate not with comets, but with ancient interstellar dust grains. For a brief moment, the astronomical community was electrified. After years of searching, here was an interstellar object, close enough to study in detail, but far more stable than the fleeting, erratic Oumuamua. Telescopes from around the world were retasked. The James Webb Space Telescope was queued for spectrographic analysis. NASA's Parker Solar Probe adjusted its observation window to catch it during its near-solar approach. Everyone wanted a piece of this traveller before it disappeared again into the dark. And then came the first surprise. The velocity data, meticulously compiled by tracking radar arrays, began to deviate. 3I Atlas wasn't simply coasting through space. Its acceleration was minutely increasing. The change was subtle, almost imperceptible, but statistically undeniable. Something was pushing it, ever so slightly, off its expected path. When scientists compared the observed trajectory to gravitational models, they noticed a tiny non-gravitational component, as if gas or vapor were gently thrusting it forward. But there was no visual evidence of such outgassing, no tail, no haze, no detectable emission line from vaporized ice. That's when the questions began. What if the object's composition allowed sublimation beneath the surface gas, building up under an irradiated crust, escaping through microscopic fissures invisible to our instruments? Or perhaps the acceleration wasn't due to outgassing at all. Could the object's shape or reflective properties be responsible? A kind of photon pressure effect. After all, light itself exerts a force, and for something with a large surface area to mass ratio, even sunlight could cause measurable drift. That was the argument for Oumuamua's strange propulsion years earlier. Was 3I Atlas showing the same behavior, or something even stranger? Weeks passed, and the object grew brighter. As it neared the sun, its surface began to reflect more light than before, not the diffuse, fuzzy reflection of vapor and dust, but a sharp, glass-like glint. It was as if something on its exterior had melted smooth, a burnished shell forming under solar radiation. Astronomers in Chile and Japan noticed that its spectrum shifted subtly toward the blue, a sign that high-energy ultraviolet light was scattering off fine-grained material or gas molecules. Yet the expected byproducts of sublimation, carbon monoxide, water vapor, ammonia, were missing. By late September, excitement had turned to unease. 3I Atlas wasn't behaving like a visitor, it was performing. Every new image made it look less like a comet and more like an engineered object. Some call that idea premature, even absurd. But others remembered how long it took the scientific world to accept Oumuamua's strangeness. After all, that object's flat shape and anomalous acceleration had forced even the most conservative researchers to admit that our models might not explain everything. Then came October. The comet entered its inbound curve toward the Sun, the phase known as perihelion approach. Its velocity spiked. Its light curve shifted again, this time in a way that no model predicted. Instruments detected a steady rhythm in the reflected light, a repeating pattern every 47 minutes. It wasn't random noise, it was consistent, measurable, and unmistakably cyclic. At first, they thought it was tumbling, rotating end over end, but the pattern didn't match rotational dynamics. It was too clean, too regular, almost as if the object were pulsing. The rhythm persisted for days, unbroken, until solar glare drowned it out. By the time it disappeared behind the sun's glare, speculation had reached a fever pitch. Theories ranged from rotational harmonics to internal thermal resonance to something that dared not be said aloud, the possibility of a signal. When 3I Atlas re-emerged on the other side of the sun in early November, the world was ready. Every major observatory turned its gaze, and that's when it happened, the brightness spike. A sudden flare, a doubling in luminosity within hours. It wasn't an explosion in the conventional sense, no debris, no shockwave, just a surge, as though the object had shed an invisible shroud. The data rolled in fast, its albedo climbed, its spectral lines shifted again, this time showing hints of carbon radicals and amidogen molecules. Something inside had been exposed. Something new was interacting with sunlight for the first time in billions of years. That was the night social media lit up with a single phrase. The comet just spoke. Of course, no one knew what that meant. Maybe it was poetic, maybe it was literal, but the timing was uncanny. Within 24 hours of the flare, low-frequency radio observatories in Australia, Poland, and South Africa reported a sudden, transient spike in the 22 megahertz band. It lasted less than 10 seconds and originated from the same celestial coordinates as 3I Atlas. The pattern was narrowband, unlike natural cosmic noise, but it didn't repeat. Scientists were cautious. It could have been a reflection of solar interference, a burst from our own magnetosphere, or even a glitch. But still, the timing. The headlines wrote themselves. an interstellar object just called home. But the truth, as always, was stranger and subtler. For the first time in recorded history, an object from beyond our solar system had brightened, pulsed, and sent back something measurable, a whisper across the cosmic sea, whether it was physics, chemistry, or something else entirely. Humanity had heard it. And as one astronomer put it, standing in front of a live feed of the glowing streak near the sun, something out there knows we're watching. What came next would turn that observation into a question none of us were prepared to answer. From the moment 3I Atlas was first plotted, its path looked wrong. Not just unusual, impossible. The software at NASA's Jet Propulsion Laboratory refused to converge on a stable orbital solution. Every time the trajectory was fit to the sun's gravity, it slipped through the parameters, diverging at the 4th decimal place like a ghost refusing to be pinned down. Comets, asteroids, even rogue interplanetary debris all obey one simple truth. Once you know their velocity and position, Newton's laws predict everything. Every future coordinate, every past encounter, all calculable. But 3I Atlas broke that pattern. The orbital eccentricity, the measure of how stretched out an orbit is, wasn't just greater than 1, meaning it would escape the sun's pull forever. It fluctuated above and below 1 depending on the time interval used. Some calculations implied a faint periodic component to its motion, as though it were momentarily influenced by something unseen before resuming its escape. At first, this anomaly was dismissed as observational error, maybe parallax from Earth's rotation, maybe solar wind pressure throwing off the measurements. But the same results emerged from observatories thousands of kilometers apart. The European Space Agency's Gaia Observatory and NASA's Deep Space Network both saw the same oscillations in its speed. Something was tugging at the interstellar object in ways no one could model. To visualize what made 3I Atlas so strange, imagine a pebble skipping across a pond. Each skip leaves ripples and arcs that follow gravity and drag. But Atlas was skipping through vacuum, a place with no drag, no resistance, and yet its path curved and corrected as if something beneath it, something invisible, was shaping its motion. As it crossed the orbit of Mars in early October, new data from radar pings revealed another oddity. Its reflective cross-section wasn't constant. In one pass, the radar echo came back strong and flat, as if hitting a broad surface. In another, it weakened dramatically, like bouncing off a narrow edge. That implied rotation, yes, but not a simple spin. The intervals between strong reflections didn't match any plausible rotation period. Instead, they seemed to shift over time, almost as though the object's shape or angle of reflection were actively changing. That realization sent researchers at Caltech and the University of Tokyo into a frenzy. They began constructing shape models, trying to determine what kind of body could produce such variable radar signatures. The answer, when they plotted the data, didn't resemble any known comet. It looked elongated, yes, but with a subtle curvature, not the jagged irregularity of rock, more like a crescent or a smooth arc. A geometry that caught sunlight differently at each angle, producing flashes of blue and white across the spectrum. Then, a second shock. When orbital simulations projected 3I Atlas backward through time, tracing its route into the Milky Way, they found it hadn't come from random interstellar drift. Its entry vector aligned almost perfectly with a known stellar stream, the Vela moving group, a collection of ancient stars moving together through the galaxy. That alignment was statistically improbable. If 3I Atlas truly originated from that stream, it had been traveling for tens of millions of years, maybe longer, detached from its birth system, but still following the faint gravitational memory of its origin. scientists began to ask, could this object have been accelerated out of its native system, flung by a cataclysmic event, maybe a collapsing planet or a dying sun? And if so, could that be why it moves the way it does now, imbued with residual momentum from a long ago disaster? By late October, the mystery deepened. High-precision astrometry from the Hubble Space Telescope recorded micro changes in its path, tiny wobbles synchronized with the comet's 47-minute light pulse discovered earlier. Each pulse seemed to correspond with a shift in trajectory, so minute it was barely measurable, but consistent enough to plot. That was impossible if the motion were purely inertial. Something was periodically pushing or pulling it. The leading theory at the time blamed internal outgassing. Maybe 3I Atlas was venting volatile material from vents that opened and sealed in rhythm. But that idea fell apart when the James Webb Space Telescope found no trace of expected gases in its near-infrared spectrum. Not CO2, not methane, not even faint water vapor. The comet was somehow exerting force without expelling anything measurable. In the community of planetary scientists, disbelief gave way to fascination. Veteran researchers who'd spent decades modeling comet dynamics admitted they were out of their depth. We're seeing behavior without mechanism, said Dr. Thea Liam of the ESA Cometary Dynamics Group. Something is applying thrust, but we can't find the source. It's like watching a candle flame with no fuel. Meanwhile, amateur astronomers across Earth joined the chase. Through backyard telescopes and live feeds, they tracked the glowing speck as it arced across the sun's glare. To them, it wasn't just an object anymore, it was a mystery unfolding in real time, a cosmic riddle visible from their own rooftops. Online forums filled with speculation. Was this solar pressure? Electromagnetic interaction? Or whispered on the edges of the internet was this guidance? On October 18, data from NASA's Stereo A probe caught something else. A faint halo of charged particles surrounding 3I Atlas, visible only in high-contrast imaging. It wasn't a dust coma, it was a plasma sheath, a bubble of ionized gas behaving like a miniature magnetosphere. That discovery turned the conversation upside down. Natural comets can develop plasma tails. Yes, but this wasn't a tail, it was a sphere, symmetrical and self-contained. The implication, 3I Atlas might be generating or sustaining an electromagnetic field. No one dared to say it aloud, but the idea circulated anyway. Could this field be interacting with the solar wind, steering the object through magnetic coupling? If so, it would mean 3I Atlas wasn't just reacting to the sun, it was negotiating with it. By the time it reached its closest approach to the sun, just 0.39 astronomical units away, every orbital model had failed. Simulations broke under their own assumptions. The parameters couldn't stay constant for more than a few hours of computation. Each time the data refreshed, 3I Atlas appeared slightly displaced, its course twisting like a thread in an unseen current. On November 1, the anomaly reached a peak. As the object passed through perihelion, the Solar Dynamics Observatory captured something astounding. A ripple in the surrounding solar corona. A shock wave, faint but real, spreading outward from 3I Atlas's path. The sun had reacted to its presence. That had never been observed before, not for any comet, asteroid, or probe. The flare wasn't solar in origin. It followed the object's wake like a bow wave in plasma. Within hours, models began incorporating magnetohydrodynamic equations, trying to explain the interaction as a solar wind disturbance. But the ripple pattern repeated when the object emerged from the other side of the sun. Two identical waves, symmetrical, timed exactly to the minute of closest approach. That symmetry defied randomness. Something about 3I Atlas's trajectory was not just mechanical, it was deliberate in its regularity. In the following days, as the object moved away from the Sun and back toward the outer system, astronomers recalculated its outbound path. The numbers were devastatingly elegant. The outbound trajectory intersected precisely with Earth's orbital plane exactly 6 days later. Coincidence, perhaps. But after weeks of chaotic motion, to suddenly align so perfectly with our orbit felt like more than mathematics. One astronomer at JPL summed it up in a message to her team. Whatever 3I Atlas is, it knows where we are. And as the object sped toward that intersection point, humanity watched the sky, waiting to see whether the encounter would pass quietly or whether the visitor from another star had come here on purpose. When the first reports of 3I Atlas's sudden brightening reached the International Astronomical Union's Minor Planet Center, even the veteran analysts didn't believe it. The initial readings seemed like instrumentation, noise, a calibration fault, maybe solar reflection from debris. But within hours, the numbers were confirmed by independent observatories across 3 continents. The interstellar object's brightness hadn't just increased, it had exploded. The change began slowly, a minor uptick in luminosity recorded on October 28th, just before perihelion. But by the morning of the 29th, it was undeniable. 3I Atlas was radiating nearly twice as much light as it had the day before. Its visual magnitude had jumped several orders beyond what standard sublimation models predicted. The sky tracking software at Mauna Kea Observatory sent an alert tagged impossible. For the first time since its discovery, the object was visible to amateur instruments. At first glance, this behavior could be explained by solar heat in the same process that ignites any comet as it nears the Sun. But the pattern didn't fit. The brightening wasn't smooth and progressive. It came in pulses, flashes of higher luminosity, peaking every 47 minutes, the same rhythm first noted weeks earlier when the object began to pulse faintly in the optical spectrum. The cycle was still there, but now amplified 100-fold, as though something inside had awakened. Spectrographs from multiple sites confirmed the transformation. The reflected light wasn't the warm yellow-white of typical cometary activity. It was blue, an electric, icy azure that grew deeper the longer it was observed. When researchers overlaid the spectrum on solar emission lines, the difference was striking. The blue shift wasn't simply a Doppler effect caused by motion. It was chemical. The dominant lines corresponded to diatomic carbon C2 and amidogen radicals NH2. Both signs of volatile release from sublimating ice, but the ratios were all wrong. Instead of a normal C, 2-2-NH2 balance, 3I Atlas showed nearly 4-1, something no known comet had ever displayed. More puzzling was what wasn't there. The telltale infrared signatures of water vapor and carbon monoxide staples of every active comet were absent. The models showed that for 3I Atlas to be shining this brightly, it should have been losing millions of tons of ice per second. Yet there was no detectable gas cloud, no tail, no haze, just a clean, glowing body, burning blue against the solar backdrop. Then the James Webb Space Telescope captured something extraordinary. During its near-infrared observation window, JWST detected narrow spectral spikes at wavelengths unassigned to any known molecular emission. The pattern wasn't random. The peaks repeated in harmonic intervals, evenly spaced, precise, mechanical. At first, researchers thought they were interference artifacts, but when the data were cross-referenced with the European Extremely Large Telescope's optical readings, the same harmonics appeared. Identical spacing, identical amplitude. That meant one of two things. Either the object was emitting radiation in periodic pulses, or the reflected sunlight was being modulated by something on its surface. Neither explanation made sense for a natural comet nucleus. Meanwhile, solar observatories monitoring in ultraviolet reported another anomaly, a faint ring of ionized gas forming around 3I Atlas. Unlike a cometary coma, this halo didn't expand or drift. It remained perfectly concentric, shimmering like a containment field. The density map revealed a consistent energy gradient, strongest at the equator, weakest at the poles. The shape wasn't random. It was organized. Within 48 hours, the global astronomical community shifted from curiosity to alarm. Research teams compared data through encrypted channels. The term coherent emission began appearing in private reports. That phrase, reserved for laser physics, radar systems, and communication technology, had never before been applied to a celestial object. The phenomenon was clear in one graph from the University of Cambridge's Cavendish laboratory. When they plotted the polarization of light from 3I Atlas, they found it wasn't scattered in all directions, as expected. It was aligned. The polarization angle oscillated with the same 47-minute rhythm as the brightness pulse, suggesting that the object's surface wasn't merely reacting to sunlight, it was manipulating it. One researcher summarized the finding in a late-night press call that was never released to the public. It's as if something is choosing when to reflect and when not to. The reaction from the scientific world was divided. Some dismissed the data as coincidence or unaccounted solar interference. Others urged caution, noting that unusual solar wind conditions near perihelion could create plasma interference patterns that mimic coherence. But those who studied the light curves closely knew better. The pulse frequency didn't match the solar rotation or flare cycles. It was too deliberate. Meanwhile, images from NASA's SOHO and Stereo A coronagraphs showed the object's form changing. For the first time, 3I Atlas appeared, stretched, not breaking apart, but elongating. The shape became more spindle-like, as though the object were drawing itself out along its axis. Yet, bizarrely, there was still no evidence of debris, no dust trail, no fragments. Whatever was happening, it was internal. At the same moment, something else occurred, something subtle but chilling. Radio telescopes monitoring the solar region began picking up bursts of low-frequency static. Unlike the brief 10-second spike detected weeks earlier, these bursts came in clusters. The first lasted 4 minutes. The second, 9. Each time, the frequencies aligned with Earth's ionospheric resonance bands, frequencies we use for long-range communication. It was as though the solar wind itself had become a carrier for information. When the signals were analyzed, they revealed a repeating structure. Not a pattern of bits, not language, but rhythm, a spectral fingerprint that matched the 47-minute cycle. Scientists compared it to the sound of a heartbeat, faint, irregular, but alive. One physicist at the National Radio Astronomy Observatory described it simply, "It's like the object is breathing." And then, in one of the most haunting moments of modern astronomy, the rhythmic brightening suddenly stopped. After 40 hours of pulsing light and blue emission, 3I Atlas went quiet. Its brightness plateaued and stabilized at a level just above baseline, as though it had exhausted its energy or completed a process we couldn't perceive. The radio bursts ceased simultaneously. When the final data was compiled, the timeline was precise to the second. The last recorded pulse occurred at 3:47 UTC on November 1st, 2025. 7 minutes later, Earth's magnetosphere registered a faint geomagnetic ripple, small, harmless, but synchronized exactly with the end of the pulse sequence. Coincidence? Perhaps, but the precision was uncanny. No debris followed. no fragmentation event. 3I Atlas simply continued on its path, now outbound, coasting away from the sun as though nothing had happened. Its blue glow persisted faintly for several days before gradually fading to its original pallor. To the naked eye, it was just another comet again. But those who had watched closely knew something irreversible had taken place. The light wasn't random. The timing wasn't chance. It had followed a rhythm, emitted harmonics, and left behind traces that could only be described as intentional modulation. In the aftermath, a single question echoed through observatories, research centres, and encrypted forums worldwide. If 3I Atlas had been silent for billions of years, travelling through endless darkness, what had just awakened it? And, more importantly, what or who had it been trying to reach? By the time 3I Atlas began its outbound drift, the world's telescopes had already turned into forensic tools. Every wavelength, every echo, every fragment of data gathered during the brightening was examined in obsessive detail. Something inside the object had changed that much was undeniable. But the question that now consumed researchers was what exactly lay beneath its skin. The first major clue came from the European Space Agency's Solar Orbiter, which had captured a high-resolution thermal map during the final hours of the brightening surge. The results were strange. Instead of a uniform temperature profile typical of a comet's surface, 3I Atlas displayed a complex grid of alternating hot and cold zones. The hottest points exceeding 700 K formed a near-perfect spiral across the mid-latitudes, wrapping around the nucleus like a helix. The colder zones, just above 100 K, filled the gaps between these bands. At first glance, this could have been the result of uneven outgassing, but the spiral's geometry was too precise. The pattern looked engineered, not eroded. It gave rise to the idea that the object's crust wasn't simply rock and ice, it was layered. Planetary scientists proposed a bold model. 3I Atlas might possess a hardened outer crust forged by billions of years of cosmic radiation, under which lay untouched primordial material matter that had never interacted with light since the dawn of its origin system. To understand why that mattered, one had to consider how interstellar objects age. Travelling through the galaxy, they are bombarded relentlessly by cosmic rays, micrometeorites, and ionized gas. Over millions of years, their surfaces become vitrified, glassy, brittle, and rich in radiation-altered compounds. The topmost layer, often just centimeters thick, becomes a kind of fossilized armor, an irradiated shell. Beneath it, however, might remain the pristine chemistry of the body's birth volatile ices, organic precursors, or even trapped gases from a long-dead star system. For scientists, this possibility was electrifying. Studying such an unaltered core could be like cracking open a time capsule from another galaxy. But 3I Atlas was no ordinary specimen. If the theories were correct, then during the brightening surge, something had punctured or destabilized that irradiated shell. The thermal spiral seemed to trace where the crust had fractured, possibly revealing patches of the ancient core beneath. Some researchers speculated that sunlight had triggered a resonance within the object, that the repeated energy pulses detected earlier weren't emitted from it, but through it. The blue glow, then, might have been a byproduct of light refracting through layers of varying density and composition, like shining a laser through sheets of glass stacked unevenly. But not everyone was convinced. At the Harvard-Smithsonian Center for Astrophysics, Dr. Leila Karani proposed an unsettling alternative. Her team analyzed the polarization data collected during the surge and found that the light reflected from the object's colder zones exhibited circular polarization, a twist in the light waves that typically occurs only when scattering off asymmetrical chiral molecules. Such molecules are fundamental to life chemistry. Circular polarization in space is rare, she explained during a closed seminar. To find it in this context suggests the crust isn't purely mineral. It contains carbon-based compounds, maybe even remnants of biological precursors baked into the shell by radiation. In simpler terms, the irradiated layer might have once been rich in organics, now fossilized and distorted by cosmic exposure. Billions of years drifting between stars could have turned once reactive materials into a glassy lattice of carbon, nitrogen, and silicate. When the sun's energy struck it, those materials could have fluoresced, creating the blue light and harmonic pulses observed during the event. Yet Khurani's hypothesis raised another problem. If organics once existed near the surface, what could have survived deeper within, shielded from radiation entirely? Theoretical simulations conducted at the Max Planck Institute for Astronomy produced intriguing results. By modelling the heat transfer from the solar encounter, they showed that beneath the outer irradiated shell, estimated to be about 3 meters thick, internal temperatures remained almost unchanged. The core was effectively insulated. Even as the surface reached several hundred degrees, the core likely stayed below 100 K, cold enough to preserve complex molecules or exotic ices. But one simulation output stood out. When factoring in the brief energy spikes during the pulse cycle, the inner core temperature briefly spiked in sync, not enough to melt, but enough to stir. This meant that energy was somehow reaching the interior faster than thermal conduction could allow. The only explanation was that the object wasn't uniform inside, it was layered with conductive veins. That discovery birthed the metallic filament hypothesis. Somewhere within the irradiated shell, scientists theorized, there could be thin conductive channels possibly formed by metallic compounds migrating under radiation stress. Over eons, as cosmic rays bombarded the surface, metals like nickel, iron, or magnesium sulfide might have diffused and fused into filaments, forming a natural conductive network. When the sun's radiation hit the object, those filaments could have generated currents enough to produce electromagnetic emissions detectable as harmonic signals. In other words, 3I Atlas might not have been alive, but it had reacted like a living system, sensing, pulsing, transmitting. Still, there was something deeper that haunted the analysis. If the pulses came from internal conductivity, then there had to be a trigger, a reason those currents started only as it neared the sun, and a reason they stopped so suddenly afterward. NASA's Goddard Center found a potential answer when analyzing magnetometric data from the Parker Solar Probe. For a brief window during the object's perihelion, a faint magnetic field appeared transient, localized, and aligned perfectly with the object's axis of rotation. The field strength was minuscule, but its orientation was deliberate. North-south symmetry, the kind seen in magnetized materials that have been polarized intentionally. Naturally, this raised uncomfortable questions. How could a naturally formed interstellar rock produce a coherent magnetic field that synchronized with its light pulses? Some suggested it was residual magnetization from formation. Perhaps the object originated near a neutron star or a strong magnetic source. Others whispered about more radical interpretations, that 3I Atlas was built, or at least altered, long before entering our solar system. Publicly, institutions dismissed those theories as science fiction. But behind closed doors, even the most grounded researchers were beginning to admit that the data refused to behave. By late November, as 3I Atlas drifted toward the outer planets, its blue glow finally faded to black. The sun's warmth no longer reached it, and its rhythm, whatever force had driven it, fell silent. But for many, the silence only deepened the mystery. If the irradiated crust was a shield, then something had been sealed beneath it, a core that had just momentarily awakened under sunlight after billions of years of darkness. And when it stirred, it hadn't burned or broken apart. It had spoken in pulses, harmonics, and light. The more scientists modelled its structure, the clearer one haunting possibility became. The blue surge hadn't been an accident. It was a response. But to what? And as 3I Atlas retreated into the void, cooling once more to silence, some wondered if it would ever be roused again, or if its true core was still waiting, buried beneath the irradiated shell, listening for another voice across the dark. For 3 days after 3I Atlas reached perihelion, space-based observatories filled with static. It wasn't the ordinary hiss of cosmic background noise. This was structured, rhythmic, and unnervingly precise. At first, it appeared as minor interference across the solar observation network, faint oscillations recorded by NASA's Stereo A spacecraft, the European Solar Orbiter, and even the Parker Solar Probe. But when independent ground-based arrays began picking up the same frequency, the story changed from a data anomaly to something unprecedented. The signals came in bursts, short, uniform pulses lasting less than a second each. They repeated at irregular but mathematically related intervals, forming a pattern that seemed to oscillate around a common harmonic ratio. For the first 12 hours, it was dismissed as instrumental crosstalk, perhaps interference from solar radiation. But when researchers from the Deep Space Network compared timestamps across 3 stations, Madrid, Canberra, and Goldstone, the pulses aligned perfectly. The delay between detections matched the speed of light across Earth's diameter. That could only mean one thing. The source was extraterrestrial, and it was real. At first, the emission appeared tied to solar wind fluctuations, as though the object was responding to charged particles striking its surface. But a deeper spectral analysis revealed something no one expected: a frequency drift matching 1,420 megahertzes, the hydrogen line. That frequency has long been considered a universal channel in SETI research, the cosmic common denominator, since hydrogen is the most abundant element in the universe. If a signal was natural, it was the strangest natural phenomenon ever recorded. If it was intentional, it would be the first interstellar transmission ever heard by humanity. The data spread quickly, though the official word from NASA and ESA was silence. The agencies neither confirmed nor denied the anomaly, but within hours, leaked telemetry from amateur radio astronomers surfaced online. A pattern had been extracted, a series of repeating tones, 8 in sequence, then a pause, then 8 again, but with one pulse missing from the third repetition. The sequence repeated for 31 minutes before stopping abruptly, coinciding with the moment the comet's blue flare reached maximum brightness. For the public, this was the spark of hysteria. For scientists, it was something worse, an unsolved equation. At the SETI Institute in Mountain View, Dr. Talia Brenner assembled a team to examine the data. "We're not talking about alien language," she said in a closed press briefing. "We're talking about physics behaving like syntax." Her phrasing became infamous overnight. What she meant was that the emissions didn't carry modulated data like a broadcast would. Instead, they carried structure, a self-organizing mathematical order embedded in noise, the kind that should not arise by accident. The spectral fingerprints showed nested harmonics frequencies related by prime number ratios. Natural emissions, like those from pulsars or quasars, tend to cluster around chaotic distributions. This wasn't that. This was discrete, layered, intentional. But what disturbed Brenner most wasn't the precision, it was the timing. The bursts synchronized exactly with the fluctuations in the sun's own magnetic field, as though the object was not just emitting but mirroring the solar heartbeat. Think of it like a conversation, Brenner said later. The sun pulses, the object replies. Then the sun pulses again, and the pattern changes slightly. It's as though the two are locked in feedback. Within 48 hours, observatories worldwide were focused on the region. China's Fast Radio Telescope, the world's largest single-dish receiver, joined the effort. FAST detected something the others couldn't, a faint echo arriving after each pulse, delayed by 2.3 seconds. The echo wasn't coming from the comet's position, it was coming from Earth's magnetosphere. At first, this was dismissed as an instrumentation glitch, but a cross-correlation showed that the echo's phase was inverted, meaning the original signal had bounced off the Earth's magnetic field like sonar. Something about the frequency was interacting with the planet itself. In other words, 3i Atlas wasn't just broadcasting, it was pinging us. That realization hit hard. Suddenly, what had been a curiosity turned into an existential riddle. If the emissions were mechanical, it implied the object could detect its surroundings. If they were natural, it meant we had discovered a self-regulating interstellar mechanism, a geological process, capable of communicating through resonance. But the strangest detail was still buried in the data. When researchers slowed the recordings by a factor of 100, the pulse structure revealed a modulation envelope faint, almost inaudible, that mapped to a rising frequency curve, similar to a Doppler chirp. Yet, unlike any signal we knew, the chirp didn't drift randomly. It formed a geometric sequence. Plotting it in 2 dimensions produced a shape eerily familiar, a spiral identical to the thermal pattern seen on 3i Atlas's surface during the brightness surge. It was the same spiral, the same rotation, the same ratio. Some called it coincidence, others didn't. Over the following week, the signal faded as the comet receded from perihelion. Yet something else began a strange behavior in Earth's ionosphere. Low-frequency bands registered faint harmonics resembling the original pulse pattern. For a brief time each night, between 2 and 3 a.m. UTC, the same hydrogen line resonance appeared, so faint that it was almost indistinguishable from background noise, but measurable, repeating, and decaying exponentially day by day. The question then became, was the object still transmitting? Or had the Earth itself begun resonating with what it heard? Dr. Brenner described it poetically. It's as if the void spoke and Earth whispered back. Skeptics, of course, were quick to offer explanations: plasma interactions, magnetospheric feedback, coincidental resonance. But the data refused simplicity. Every known model of solar radio reflection failed to reproduce the harmonic nesting. The energy levels were too consistent, too organized, too deliberate. And then, 2 days after the final echo vanished, NASA's Deep Space Network at Canberra received a narrowband ping, not from 3i Atlas's last known position, but from the opposite direction, a point in space exactly aligned with the path it had entered from months before. The signal lasted less than a second. It carried no message, no modulation, just a sharp, clean pulse. When triangulated with other receivers, the signal's source lay far beyond the heliosphere, an origin impossible to verify. But one thing was certain: it came from interstellar space. Officially, the agencies said nothing. But off the record, more than one researcher referred to it as the reply. And that's when the narrative shifted from astronomy to philosophy. For the first time, humanity had possibly witnessed an object from another star listening to us and responding not through language, but through the universal grammar of physics. If 3I Atlas had truly spoken, then it did so using the only medium that every civilization, every atom, and every star understands: resonance. But as the object faded into the darkness, something else was left behind, a subtle, persistent radio hum near the hydrogen line, still detectable weeks later, not strong enough to decode, not random enough to ignore. It was almost as if the signal hadn't ended, it had just changed carriers. Perhaps the message wasn't sent through light at all. Perhaps it was written into the field itself, a resonance now intertwined with the electromagnetic breath of our own planet. And somewhere beyond the heliopause, 3I Atlas kept moving, silent again, its irradiated shell dark and cold. Yet for those who had heard the brief whisper across the void, one truth lingered. Something out there had noticed us, and whatever it was, it had spoken first. In every textbook, comets are predictable. They follow elliptical paths, brighten near the sun, shed dust, grow tails, and fade into the dark. They are relics, frozen archives from the birth of solar systems. But 3I Atlas, it tore that rulebook apart, page by page. Even before perihelion, astronomers were uneasy. The object's light curve didn't match any known model. Instead of a smooth, steady rise in brightness as it neared the sun, it fluctuated, violently pulsing like a heartbeat. Then, just when every simulation predicted a dust plume, nothing happened. No tail, no coma, just a faint, unnervingly clean glow. By the time high-resolution imagery came in from the SOHO and Stereo A observatories, confusion turned into disbelief. 3I Atlas wasn't trailing dust at all. Its structure appeared streamlined, almost aerodynamically, so a spindle rather than a sphere, reflecting sunlight unevenly as it rotated. The absence of dust wasn't just strange, it was impossible under normal cometary physics. Every comet heats up as it approaches the sun. Ices sublimate, gas escapes, and with it comes dust, the signature tail that defines a comet's identity. Yet 3I Atlas refused to play by those rules. Dr. Eric Jensen of the European Southern Observatory summarized the frustration bluntly. It behaves like a comet, looks like an asteroid, and moves like neither. Spectroscopic readings only deepened the mystery. Most comets in our solar system release familiar volatiles: water, carbon monoxide, carbon dioxide, methane. But 3I Atlas's emissions painted an entirely alien profile. Yes, there was water, but in wildly unstable ratios, surging and collapsing unpredictably, as if boiling beneath a fractured lid. Alongside it, scientists detected molecules rarely seen in comets: amidogen, NH2, diatomic carbon, C2, and something that caused even veteran chemists to blink twice: faint traces of cyanogen and nitrile radicals that shouldn't have existed under the measured temperatures. The readings didn't match the heat, they didn't match the radiation exposure, they didn't even match each other. The chemistry was chaotic. NASA's Goddard Space Flight Center ran computer models to simulate outgassing patterns based on the recorded spectra. None of them fit. The data suggested that the nucleus was undergoing rapid chemical cycling, decomposition, recombination, and re-release all within minutes. A comet's core is supposed to be inert until heat triggers sublimation, not an active chemistry lab fluctuating like a reactor. What could drive that kind of instability? The leading hypothesis centered around something called phase heterogeneity. Unlike our solar comets, which formed from the same protoplanetary disk and contain relatively uniform ices, 3I Atlas originated from another star system entirely. Over billions of years in interstellar space, cosmic radiation, could have fractured molecules, embedding reactive fragments throughout its crust. When sunlight finally reached it, those fragments might have recombined explosively, producing sudden chemical storms. It wasn't just outgassing, it was autocatalysis. That meant the comet wasn't melting, it was reacting. And each reaction might have triggered the next in cascading waves that propagated through its core, like chemical lightning. To test this, researchers examined infrared readings from the James Webb Space Telescope captured during the perihelion event. The Webb data revealed microbursts of temperature spikes, tiny, rapid heat surges appearing and vanishing across the surface. The bursts were too localized and too fast for normal sublimation. They were more like flare points, small explosions of trapped volatile compounds reacting violently when exposed to sunlight. And then came the truly strange part. The heat signatures weren't random. When plotted over time, the bursts formed spiral patterns, the same geometry found in its earlier spectral emissions, and in the pulse map described by SETI teams, the comet's chemistry, it seemed, was not chaotic at all. It was organized chaos. Something inside the nucleus was responding to solar energy with a kind of order, but not biological order, not mechanical, something chemical and emergent, as if the matter itself had learned to self-regulate after billions of years of survival in interstellar space. It's like a feedback loop, said Dr. Leila Kourani, who had earlier studied its irradiated shell. The comet's surface reacts to sunlight, triggers internal energy releases, which then alter the way it reflects light, as though it's protecting itself, adapting on the fly. Her words sparked heated debates. Could an interstellar object display quasi-adaptive chemistry? Could non-living matter evolve to learn stability through radiation exposure? The argument was not without precedent. In materials science, radiolytic adaptation refers to the way compounds change molecular structure after repeated exposure to high-energy radiation, gradually forming more stable configurations. In interstellar timeframes, those processes could lead to emergent self-regulation, even something that appears alive. But whatever the explanation, 3I Atlas wasn't just odd, it was rewriting cometary science. Consider its shape. Based on photometric light curves, astronomers estimated its rotation period at roughly 14.2 hours, but with a non-uniform axis wobble that defied physics. The spin rate fluctuated, sometimes slowing, sometimes accelerating, without any external torque visible. No jets, no dust ejection, nothing to explain the angular changes. In short, the comet was changing its spin without losing mass. That should be impossible. Unless, of course, there were internal density shifts, masses moving inside. If that were true, then 3I Atlas wasn't a rigid body at all. It was dynamic within fluid, pockets, cavities, maybe even interconnected chambers. The missing dust tail suddenly made sense. The volatile material wasn't being expelled outward. It was being redirected inward. The comet might have been venting through internal channels, trapping its own gases in a pressure feedback system that fed its brightness from within. That would also explain the sharp spectral bluing light scattering through internal ice and gas, rather than an external coma. Essentially, it glowed from inside out. When researchers ran 3D density simulations using Webb's infrared data, the internal model came back as hollow, not completely, but riddled with tunnels and cavities. The core density was 38% lower than expected. It looked like something had carved paths through it, paths aligned with the spiral thermal patterns seen earlier. At that point, comet became a label of convenience rather than accuracy. Even conservative scientists began calling it what it really was, an unknown class of interstellar object. In an emergency symposium held by the International Astronomical Union, veteran cometologist Dr. Ren Ito summed it up. We have to stop pretending 3I Atlas is a comet. It doesn't sublimate normally. It doesn't eject dust. It doesn't rotate properly. and its chemistry doesn't stabilize. It's a self-organizing structure made of volatile compounds, not a remnant of a solar nursery, but a survivor of deep time. And that survival came with consequences. Because if 3I Atlas had endured cosmic radiation for billions of years, it might have done so by developing these reactive feedback systems chemistry that heals, resists, and evolves. In essence, 3I Atlas had broken every cometary law, not because it was failing, but because it was adapting. As it left the sun's influence, the object's activity dropped sharply. The internal glow faded, its brightness normalized, and the spectral emissions stabilized as though the chemical storm had gone dormant again. It returned to silence. But in that brief outburst near the sun, humanity had seen something profound. Matter behaving intelligently, chaos organizing itself, and a comet rewriting the physics of what it means to exist between stars. Some scientists whispered that perhaps the reason 3I Atlas had no dust tail was simple. It had learned long ago that losing mass meant losing itself. And so, instead of dying like every other comet, it had evolved to endure. Long before 3I Atlas entered the inner solar system, it was something else entirely, a relic of a time before our sun even formed. To trace its origins, scientists had to look backward through billions of years of cosmic history. Every molecule, every isotope embedded in its icy shell carried the imprint of a distant sun, a long-gone world, and a violent birth. When researchers modelled its chemical composition as much as they could infer from its spectral readings, they found a disturbing mismatch. Certain organic molecules present in its coma shouldn't exist in the ratios detected. The hydrogen isotopes, the carbon to nitrogen ratios, they belong to an environment far colder, far older than any known comet in our system. Some of its volatiles were more akin to those found in molecular clouds, regions of space where stars are still being born. It suggested one thing: 3I Atlas wasn't a child of any star we know. It may have formed in the outskirts of a system that died before ours ever lived. Somewhere in a forgotten corner of the galaxy, a young star flared too brightly, its gravity too chaotic. In that moment, debris was cast outward, and one fragment, this one, began its slow exile into the interstellar dark. Its first transformation came from radiation, the slow, merciless kind that only deep space can deliver. Over billions of years, cosmic rays bombarded it, turning the outer layers into something like armor. The once soft ice crystallized, polymerized, and eventually became a carbonized shell, kind of space fossil skin. Beneath it, untouched volatiles and ancient organic materials slumbered, preserved in temperatures barely above absolute zero. But the real metamorphosis didn't begin until it met light, again ours. As it crossed into the heliosphere, sunlight began seeping into that ancient shell. For the first time in untold ages, 3I Atlas began to wake. But it didn't react like any ordinary comet. Instead of simply venting gases in predictable jets, it pulsed. The light curve suggested uneven heating, massive subsurface pressure pockets opening in bursts. The whole body seemed to throb like something struggling to breathe after eons of stillness. The pressure waves that followed didn't match typical outgassing behavior. Some even seemed to reverse direction, implying that material wasn't just leaving the surface, it was being reabsorbed. To some observers, it looked like feedback, as if the comet was regulating its release rather than losing control. The hybrid nature of 3I Atlas became clearer with each observation. Spectroscopy revealed silica grains that shouldn't survive interstellar travel. Its albedo shifted, reflecting light more efficiently over time, a sign that its surface was self-modifying. The mix of organic residues and mineral inclusions hinted at a phase transition: ice to dust, dust to glass, glass to something else entirely. There was another oddity. Radar signatures showed that parts of its nucleus were unnaturally dense. Some estimates placed the central core's density higher than any known comet, perhaps rivaling that of metal-rich asteroids. It was as if a rocky heart had grown beneath the ice, or had been encased within it long ago. The transformation didn't just occur on the surface. The chemistry within its coma began to evolve dynamically. Photochemical reactions fed on the sun's radiation, creating new compounds in real time, some of which decayed too fast to ever reach the instruments on Earth. Scientists likened it to watching an organism adapt on a molecular scale, rewriting its own formula with every rotation. And then came the behavior that no one could fully explain, the stabilization event. After weeks of erratic tumbling, 3I Atlas suddenly slowed its spin. The chaotic wobble ceased. Its rotation axis aligned almost perfectly perpendicular to its trajectory. To any physicist, this looked like self-correction. Objects don't just do that on their own unless internal mass redistributes, or unless something deeper governs the motion. It became the point of division among researchers. One camp argued for physics, latent heat pockets shifting the mass balance. The other dared to whisper the unscientific, that something inside 3I Atlas was responding to external forces, perhaps even intelligently. Most dismissed that notion, but the data kept forcing uncomfortable questions. What if the object was never meant to behave like a comet? What if it was designed to appear as one, a disguise, an adaptation? 3I Atlas, at that moment, became more than an astronomical curiosity. It became a symbol of transformation itself, a cosmic wanderer reawakening after eons of dormancy, reshaping itself as it approached the sun's warmth. Every frame of telescope footage seemed to tell the same story. A thing learning how to be alive again. And yet, the more it changed, the less it resembled what it once was. Its orbit deviated slightly from predictions after the brightening surge. Its mass estimates shifted inconsistently, implying that material loss and gain were happening simultaneously. Astronomers began to describe it not as a comet or asteroid, but as a process, something caught between states, perpetually reinventing itself. Whatever 3I Atlas had been when it was expelled from its parent system, it was no longer that. The universe had reshaped it, and now, in the quiet brilliance of our star, it was reshaping itself again. No one could tell where the transformation would end, or if it ever would. But one thing was certain: when it finally left our solar system, it would not be the same object that entered it. It would carry traces of us, our light, our radiation, our brief moment of attention burned into its evolving form. The question that haunted the scientists most wasn't what 3I Atlas was, but what it was becoming, and if it was changing because of us or for us. The deeper scientists probed into 3I Atlas's spectral data, the more it began to read like a biography of another world. The isotopic signatures were unlike anything seen from a solar-born body. Ratios of deuterium to hydrogen, oxygen 1,7 to oxygen 1,8, and the balance of carbon isotopes, all whispered of an environment colder than the Kuiper Belt, older than the Oort cloud, and far more chemically exotic. It was as though the object carried a frozen record of a star that had long since gone silent. Through the lens of spectroscopy, every molecule became a clue. The methane and ammonia levels were abnormally low, while complex nitriles, precursors to amino acids, spiked in strange harmonies. On Earth, those molecules form only in interstellar dust clouds, bathed in ultraviolet light. This suggested that 3I Atlas had not been sheltered within a planetary nursery like ours, but had gestated in the raw edges of a star-forming nebula where radiation sculpts chemistry into its most alien forms. From these fingerprints, astrochemists attempted to reconstruct its birthplace. The ratios implied a star system whose central sun burned cooler and smaller than ours, perhaps a red dwarf wrapped in an envelope of icy debris. Somewhere in that ancient system, gravitational tides must have jostled planets and comets alike, flinging one wanderer free. If that star still lived, it would now lie tens of trillions of kilometers away, invisible even to our best instruments. The dust trapped within 3I Atlas's coma carried further revelations. Some grains exhibited crystalline structures that can form only in regions close to intense heat, far closer to a star than an ice body could normally survive. Others were amorphous, frozen into place in deep cold. This contradiction meant that material from both the inner and outer reaches of its native system had been mixed together, then expelled as one fragment. In short, 3I Atlas was a composite, a traveller assembled from multiple worlds. When the Atacama Large Millimeter Array captured its faint emissions in sub-millimeter wavelengths, a new pattern emerged. The spectral lines indicated an overabundance of sulfur dioxide and formaldehyde, both sensitive to ultraviolet radiation. These were markers of a system where the parent star had gone through violent youth, flaring, pulsing, seeding its surroundings with unstable energy. 3I Atlas was forged amid chaos, not calm. The isotopic evidence also hinted at stellar death. The ratios of certain oxygen isotopes matched those found in supernova-polluted nebulae regions enriched by exploded stars. It suggested that the material forming 3I Atlas had once drifted through the ashes of a dying sun, absorbing heavy elements forged in that final burst. In that sense, it carried within it not only the memory of its own world, but the ghost of another that perished before it. To planetary scientists, this was more than a chemical curiosity. It was a time capsule from beyond our cosmic neighborhood, proof that the same elemental recipe that built us carbon, hydrogen, oxygen, nitrogen exists everywhere, recombining in endless permutations. The discovery of certain organic radicals within its coma reinforced a long-held suspicion. Life's ingredients are not rare. They are the universe's default setting. But there was another lesson hidden in the data. When researchers simulated the thermal history of 3I Atlas, they found that its composition could only survive if it had spent most of its existence in interstellar space, drifting in temperatures near absolute zero, shielded from radiation by that hardened crust described in earlier chapters. That meant it had crossed between stars for millions of years, untouched, carrying intact samples of matter from its original system. For the first time, humanity was studying alien geology without leaving home. The results began to challenge long-standing models of planetary formation. If 3I Atlas's mixed composition was typical, then protoplanetary disks might be far more turbulent than previously imagined, capable of hurling matter from inner regions to outer edges in violent exchanges. Planets and comets in other systems may not form neatly in layers, but in collisions, an interstellar version of creative destruction. Even more puzzling were the molecular bonds that appeared resistant to solar radiation. Compounds that should have broken apart under intense sunlight remained stubbornly intact. Some theorized that cosmic irradiation during its exile had altered its chemistry, giving rise to self-stabilizing molecular lattices, a kind of radiation-hardened organic glass. Others saw in this resilience a metaphor. Perhaps nature itself was built to wander, to adapt to any light it encounters. The object thus became a window not only into another system's birth, but into the resilience of matter itself. Each analysis blurred the boundaries between foreign and familiar. The carbon that formed in a distant sun now burned blue under ours. The ice that once orbited an alien world sublimated in our heat. And in that transformation, 3i Atlas reminded us that the universe recycles endlessly, stars dying to feed new worlds, matter migrating from one sky to another. Somewhere within the telescope data, amid the noise and background radiation, astronomers found a subtle rhythm in the way its emissions pulsed. To most, it was nothing more than thermal cycling, the periodic breathing of an object thawing and freezing. But to a few, it sounded like memory, a remnant pattern carried across light years, a faint signature of the star that once warmed it. When scientists speak of windows into other star systems, they usually mean mathematical ones, equations, models, simulations. But 3i Atlas offered a literal window. It passed close enough that its gases brushed the solar wind, and for a brief span of days, particles from two different suns danced together. Instruments on Earth caught that mingling, alien dust meeting our own plasma, exchanging charge, reshaping each other. It was chemistry at a cosmic scale, two histories touching, then parting forever. And as 3i Atlas arced outward once more, its spectrum shifted again, as though the light it reflected now carried a blend of both worlds. The scientists who tracked it began to speak of it in different terms, not as an intruder, but as a messenger. In its silence, it had told us more about creation than any telescope could dream to show. When it finally slips beyond Neptune's orbit and vanishes into the dark, it will take with it traces of our sun's radiation and our curiosity, our fingerprints on its surface. And somewhere, light years away, when another civilization detects that same faint traveller, they may read in its spectrum the story of us, just as we read the story of them. Because that is what 3i Atlas ultimately is, a bridge between stars. A reminder that the boundaries we draw between systems, worlds, and species are illusions. In the vast, unending exchange of matter, we are all visitors, all fragments of some earlier explosion, still travelling, still transforming. As 3i Atlas receded from perihelion, astronomers expected the drama to fade. Most comets dim as they move away from the sun, their volatile gases exhausted, their chemical reactions slowed. But 3i Atlas had never followed normal rules, and post-perihelion observations confirmed it would not start now. Within days of leaving the inner solar system, the first surprises emerged. Light curves, expected to decay gradually, instead showed intermittent spikes. Brightness would plateau, then climb unpredictably before dropping again. Each spike lasted hours, sometimes minutes, with no correlation to solar activity or rotational phase. Something inside the comet remained active, alive, in a sense that defied explanation. Space agencies scrambled to track the object. NASA's Deep Space Network, ESA's Gaia mission, and even the Chinese CNSA's Tianwen arrays redirected instruments to maintain a constant vigil. Unlike typical comets, which could be observed passively, 3i Atlas required coordinated, multi-wavelength monitoring to catch each fleeting anomaly. One particularly puzzling event occurred in early November. A sudden flare increased its brightness by nearly 15%, accompanied by a surge in carbon-based spectral emissions. Ground-based telescopes in Chile and Hawaii reported weak infrared echoes consistent with a delayed thermal pulse, as if the core had absorbed energy and released it later. This was no longer outgassing in the usual sense. This was a deep internal process. Radio observatories also reported anomalies. A faint harmonic at 1420 megahertzes, the hydrogen line previously associated with its perihelion pulses, reappeared intermittently. Unlike before, the echoes were weaker but persistent, suggesting that whatever had produced them might still be resonating, perhaps using its own irradiated crust as a conductor. Dr. Talia Brenner, who had analysed the perihelion signals, called this the ghost of the conversation, faint, ongoing, and nearly impossible to interpret. Meanwhile, trajectory analysis revealed subtle deviations from predicted paths. Even tiny non-gravitational accelerations, common in comets due to jetting, could not fully account for the observed motion. Models incorporating variable internal mass distributions fit the data better, implying that something inside the object remained mobile. Its core was likely still reorganizing, adapting, or even breathing as it had near the Sun. The James Webb Space Telescope continued infrared monitoring, capturing another mystery: temperature fluctuations across the nucleus that seemed synchronized with spikes in reflected light. Some areas cooled rapidly, while others heated in sudden bursts. Researchers called this thermal intermittency, a behavior entirely without precedent. Some simulations suggested that volatile pockets buried dozens of feet beneath the irradiated crust were undergoing sequential sublimation, a cascading chain reaction propagating through the comet's interior. At this point, the scientific community faced a dilemma. Conventional comet science could not explain these observations. Some proposed that 3I Atlas might be a hybrid object, part relic, part emergent system, part unknown physics. Others cautioned against overreach, attributing anomalies to measurement, artifacts, or unmodelled sublimation. But with every new dataset, the evidence leaned toward the extraordinary. This object was still evolving before our eyes. Amateur astronomers, though unable to see 3I Atlas directly, contributed by tracking faint photometric variations using small telescopes. Their observations often matched professional data, confirming that the fluctuations were real, not instrumental errors. The global scientific effort became unprecedented. Literally thousands of observers coordinated across continents, focusing on a single interstellar object. The excitement wasn't limited to astrophysics. Planetary defense teams began running simulations to understand what 3I Atlas could do if a similar interstellar visitor approached Earth more closely. While this comet posed no immediate threat, its unpredictable activity underscored the limitations of existing models. If an object could reorganize internally, accelerate unexpectedly, or release bursts of material without warning, predicting its path decades in advance became a challenge. In private briefings, a few researchers began speaking in cautious, speculative terms. The Sun was only the first test, one scientist said. We may be observing a kind of interstellar evolution processes that require proximity to a star to manifest. Another noted that the pattern of emissions, both optical and radio, might extend beyond our system entirely, hinting at phenomena we have never categorized. Perhaps most intriguing was the question of timing. Post-perihelion, 3I Atlas seemed to delay certain reactions, waiting days or weeks to release energy impulses. It suggested that the object's internal processes operated on cycles we barely understand, a rhythm of interaction between its irradiated shell and the hidden core. The comet's behavior now resembled a celestial symphony, with crescendos and quiet passages, each note unpredictable yet structurally coherent. Some astronomers have begun to wonder if we have only witnessed the beginning of 3I Atlas's story. Its journey through the solar system might be a multi-year event, with phases of brightness, radio pulses, and chemical evolution yet to be revealed. Every observation generates new questions. What will happen as it crosses the orbit of Jupiter or Saturn or beyond? Will internal pressures eventually fracture the nucleus? Could the object reveal pristine material from its original star system once more? Monitoring missions have been proposed. Concepts include solar sail probes that could match velocity for a flyby, advanced radio arrays dedicated to long-term surveillance, and even space-based coronagraphs to watch subtle changes in reflectivity. Funding and technology constraints make these projects difficult, but the scientific incentive is unparalleled. 3i Atlas is a moving laboratory, a direct sample of interstellar chemistry, physics, and potentially unknown processes. For now, all that humanity can do is watch and record. Telescopes track its trajectory, spectrometers measure its light, and radio arrays capture echoes. Each pulse, each flare, each temperature spike is catalogued, waiting for patterns to emerge, a cosmic diary of a visitor from another star, continuing to challenge our understanding of matter, chemistry, and celestial behavior. In short, the unknown ahead is vast. 3i Atlas may fade into the darkness, or it may continue to surprise, revealing new phenomena with every degree of distance. Unlike any comet in history, it refuses closure, teaching a hard lesson. When interstellar matter enters our system, the universe's rules may bend, adapt, or even break entirely. And as astronomers keep their eyes fixed on the distant points of light, one truth crystallizes: we have not yet seen the final act. The real show, the evolution, the mysteries, the revelations, may still be unfolding. 3i Atlas is not just a scientific curiosity. Its journey through our solar system, the chaotic chemistry, the strange pulsars, the missing dust tail, all of it converges into a profound lesson about the universe and our place within it. For centuries, humanity has looked at comets as passive witnesses to cosmic history, frozen, inert relics that record the infancy of stars and planets. 3i Atlas refuses that narrative. It is active, dynamic, and almost responsive. Its presence forces us to reconsider what we thought we knew about matter, life, and survival across cosmic time. The first implication is scientific humility. Here was an object that challenged everything astronomers had assumed about interstellar visitors. The textbooks on cometary physics were suddenly insufficient. Models that predicted brightness, tail formation, rotation, and chemical output all failed. Observatories scrambled to recalibrate, and yet no single theory could account for all observations. 3i Atlas reminds us that the universe is vast and far more inventive than our theories allow. Each equation we write, every simulation we run, is only a shadow of reality, and sometimes the shadow fails to reflect the truth. Then comes the philosophical impact. 3i Atlas is, in many ways, a traveller of survival. It spent billions of years alone in interstellar space, bombarded by cosmic rays, exposed to nothingness, yet endured. Its irradiated crust and self-regulating chemical processes are evidence not just of physics, but of resilience, a cosmic example of how matter can adapt to the harshest of environments. That has a subtle, humbling echo for humanity. If inanimate matter can persist across time and space, bending and reshaping itself to survive, what does that imply about our own potential for resilience, adaptation, and transformation? Its chemical composition, too, has profound significance. The isotopic signatures, the exotic organics, and the mixed dust grains are windows into star systems we will never visit, revealing the processes that shape planets, moons, and potential life elsewhere. 3i Atlas carries the fingerprints of other suns, other nebulae, other histories, proof that the building blocks of planets and life are universal. Each molecule it releases, every photon it reflects, expands our understanding of how common or rare the conditions for life might be across the galaxy. It is a literal bridge to other worlds. And yet, there is an existential dimension. 3I Atlas forced humanity to confront unpredictability on a scale few events ever have. It arrived without warning, behaving in ways no one could fully anticipate. Its internal processes, the irregular pulses, the deviations in trajectory, all suggest that the universe does not conform to our expectations. This object is a living reminder of the thin boundaries between the known and the unknown. For a species that craves certainty, 3I Atlas demonstrates that curiosity and openness are more valuable than confidence in familiar models. There is also a symbolic aspect. The fact that the comet carried signatures of a distant star system, travelled billions of years through voids, and now passed through our neighbourhood connects us to a cosmos far larger than ourselves. It is a tangible expression of cosmic continuity. Matter moves, survives, transforms, and connects distant points in ways we are only beginning to comprehend. Each photon of its blue glow that reached Earth carried a message from a system that predates our sun, a whisper of the vastness beyond our imagination. From a practical standpoint, 3I Atlas challenges space science in ways that will shape research for decades. Monitoring missions, improved telescope networks, and spectroscopic surveys will all take cues from this object. It has set a benchmark for interstellar object studies, showing that classification based on our solar system is insufficient. Scientists will develop new models, simulate long-term interstellar survival, and reconsider planetary defense strategies, because unpredictability is now a fundamental property we must plan for. Finally, there is a sense of wonder that cannot be quantified. The public response, from amateur stargazers to professional astronomers, has been electric. For a brief time, humanity watched a visitor from another star system, a relic, a survivor, and a mystery, unfold its secrets before our eyes. That sense of connection, of witnessing something entirely alien yet tangible, touches something deep within us. 3I Atlas reminds us that we are not alone in the cosmos, not in the sense of intelligent life necessarily, but in the continuity of matter, energy, and the forces that shape existence. In the end, 3I Atlas matters because it teaches lessons that no simulation, no theory, and no lab experiment could ever convey. It embodies the unpredictable genius of the universe, the resilience of matter over time, and the possibility of learning from things that are not of our world. It forces us to expand our definitions of life, of persistence, of intelligence, and of survival. We cannot yet answer all the questions it poses. We may never fully understand its chemistry, its internal structure, or the rhythms that guided its behavior. But by observing, documenting, and thinking critically, we take the first steps in a conversation that began billions of years ago with a star system far away, and now with us. As 3I Atlas drifts back into the cold reaches of the galaxy, its story lingers. It leaves a trail of data, mystery, and inspiration. It challenges our science, expands our philosophy, and ignites our imagination. It is a reminder that the universe is not a static backdrop, but an active participant in its own narrative, one that we are privileged to witness, if only for a fleeting moment. And perhaps, somewhere in the darkness between the stars, 3I Atlas will continue to evolve, to transform, to pulse, carrying with it the legacy of its home system and now a memory of us. In the end, its journey is not just about a comet. It is about curiosity, resilience, and the endless capacity of the cosmos to surprise. 3I Atlas arrived from the dark, it spoke in light and chemistry. And through that language, humanity has heard a message that the universe is stranger, older, and more interconnected than we have ever dared to imagine.